In this video, we're going to have an introduction to binary trees, why we do them and what some of the values of them are. Okay, so this one is not going to be particularly code heavy. There are lots of examples of code. So instead, we're just going to talk about some of the theory and some of the ways we're going to approach this problem and some of the things that it could solve. Okay, so let's start with the definition of a binary tree. Okay, so we're going to say a binary tree, make this a very formal definition. We're going to say that one, a binary tree, let's say T is our tree, has a special node called the root node. Okay, so you'll see as we go along that this is going to be similar in many ways to a linked list. Okay, we'll make some differences between them here. Okay, two will be that T has two sets of nodes. Okay, we call this LT and RT, which are the left and right subtree. I'll say about the subtrees, next word there. Okay, and then three, LT and RT are also binary trees. Okay, so that's the formal definition. So what does this mean in practicality? Okay, so my Apple pencil has died, so I'm reduced to drawing with my mouse, which is not great, but hopefully we get the idea. Okay, so if we have a node, now the node that we did for linked list, we drew like this. We had some data up here. That will be true. Okay, where we had one link before, we're now going to have two links. Okay, so one link is going to go to the left. Have another node there. And then one is going to go to the right. Okay. And each of these will also have a left and a right. Okay. So again, we would refer to this as the left tree, and however far that goes down, and the right tree. Okay. Each of these are also trees. Okay. So the binary means there are two. There's a left and a right. Okay. That's all there is to it. So it's kind of like if you were to take a linked list. Okay, so let's clear this out and start over again a bit. If you were to take a linked list of items here and then kind of pull one up, okay, into this kind of we can do circles to make it easier, in this kind of hierarchy in some way, okay, where our nodes could be connected in this way. Okay. And similar to other data structures we've talked about, all we're going to keep track of is going to be the root node, and then we'll have to follow along in the direction of the arrows, okay, in order to get to all the other nodes. Okay, so it works like a linked list, except that it's got two things we're doing, and it has this hierarchy, which we don't have with a linked list. Okay, so when we're doing the code itself here, we're going to have a little bit of a change. Okay, so we have, if we're doing a templated, so if we have template or class, element type, whatever we want to call that. Okay, we have a struct as we've had before. We're going to call this a binary tree node. Okay, the struct is going to have the following. It's going to have something of whatever type it is, element type info, okay, that will hold the data for this node. Okay, it's then going to have two binary tree node element type room pointers called link and, surprisingly enough, what is that doing? Good Lord. I lost my way. Yeah, that totally died. Don't know why. That is really unfortunate. Now you can't go back. I guess I'll type it again. So we have our, I'm going to go ahead and make it bigger. You know, I don't love not having my Apple Pencil. So we have our binary tree, node, lm type, link, and our binary tree, node, lm type, pointer, or R link. So that's a structure we're going to use. Okay. So whatever data we're storing will be an info. We could either make it a tree of integers, a tree of strings, a tree of chars, whatever it is. Okay. And we'll have a pointer to the left node and a pointer to the right node. Okay. So a lot of the things that we've conceptualized with our linked list are going to be as you would expect. Okay. So we have some different terminology we're going to use here with our trees. Okay. So the first thing that we're going to have, so we have our, that's what I want. We have our pointer root. We have a series of nodes that have whatever data they have at the left and right, and go on in both directions. Okay. So put an A here. We say that if a node has no children, it's called a leaf node. Okay. And we also talk about a parent, a grandparent, sibling, all those things. Okay. So in this case, B and C are both leaf nodes. A is the root node. A is the parent of B. B is the child of A, and B and C are siblings. Okay. We can talk about the level of a node. Okay. It's the number of branches from the root to the node. Okay. So these are going to be at level 1 if they had a child. It would be level 2 and so forth, because there's 1, 2 links back to root. Okay. Then we talk about the height of a binary tree. It's the number of nodes on the longest path. Okay. It doesn't have to follow any orderly fashion. So if we go down to here for an E, we can even put F back this way. Perfectly legal to do this. Okay. So then 1, 2, 3, 4. So the height in this case would be equal to 4. Okay. So just some basic definitions. There's some ways that we can find that. Okay. So like other data structures that we've talked about, we have to be concerned about aliasing. We have to be concerned that when we go to either assign something with the equal sign or to use a copy constructor, that we're getting everything. Okay, so we're going to have to go through and recursively, it's going to be the only real way, or the easiest way to do it. We're going to recursively copy all of the nodes of the tree. Okay. One of the other big things we talk about in binary trees is the idea of the different traversals that we can do. Okay. So the traversals here, I think I'll probably want to write these out. Traversals then, there are 3 types. Okay. Type 1 is the in-order traversal. And it is traverse the left subtree. We then visit the node. And then we do traverse the right tree. Okay. So if you look at the tree I've drawn up here, okay, it's bizarre and strange as it is, we always start at the root. Okay. So visit means you add it to your list of things. You got to go through the whole tree. Okay. So this in order traversal means we start by traversing the left tree. Okay. I traverse the left tree. I'm now at B. When I'm at B, I start over again. I traverse the left tree. I'm now at D. Okay. I can't traverse left anymore. I visit the node. So D is the first one in my traversal. Okay. We've now marked that off. Okay. So visit the node, traverse the right. I traverse the right to E. I'm now here new, go back to 1, traverse the left, and now F is the second. Okay. I try to traverse the left here, I can't. Visit the node, mark it out. Should change colors. So now this has been visited, and this has been visited. Okay. I'm at F, I visited the node, traverse the right, doesn't happen. So now when I'm done, so now I've done all 3 of these, I go back to where I came from. I go back to E. So I've done this one for this version of E, or this version of the traversal. Okay. I now visit the node. Okay. So then the E gets put in here. Switch colors back. The E is a next. Okay. Now that's visited. Okay. Now we try to traverse the right, no right. So we're done. We go back to here, back to the D node. Okay. We've already done the left. We've already visited the node. We've already done the right. So now we're done here. Now we're back to here, back to B. Okay. And B, we traverse the left, but that's all we were able to do. So now we can visit the node, B, wrong color. Okay. Then I'm able to mark that one. Okay. We then try to traverse the right. There is no right. Okay. Now we're back to A. Okay. So with A, we've traversed the left already. These are recursive calls. So we're now back to where we were. Okay. Time to visit the node, A. Okay. So we've now visited A. Mark it as visited. Okay. And finally, we traverse the right, takes us to C. We traverse the left, nothing there. So we visit the node, the C. Okay. So that's marked. Visit the right, and we're done. Okay. So that's the in order traversal. The visiting the node is the only difference on those. Okay. So for the pre-order traversal, we do a visit, then left, then right. Okay. So the pre-order traversals always start with the root node. Okay. So we visit, then we go left. Okay. We've gone left. So now we're at B, we're at a new node. So again, we do a B. Okay. And we're going to keep going along in that fashion. Okay. A visit, then left, then right. Okay. And then finally, the post order will be a left and then right, and then visit the node. Okay. So in that case, we start at A, we go left, B, left, D, try left, can't do that, go right. Okay, now we're at E, left, only when we're at F. Okay, so in a post order, your F becomes the first node that you visit. Okay, so it's always variations of those 3 different tasks of traversing left, traversing right, visiting the node. And again, I think what gets people confused is that every time you traverse to a new node, you have a new version of these instructions. You start back at 1, okay, until those are closed out. Okay, and those traversals turn out to be pretty helpful for us. Okay, so again, I'll do another video. We'll talk more about the coding. I wanted to get it out there, just some basic ideas of what's going to happen. Okay, so as we go about implementing a binary tree, again, we've got our struct that we use with the nodes, and then we're going to progress kind of like we did with the linked list. We're going to have the different things that we can do with our trees. Okay, so we're going to have it as empty. We're going to have our traversals, our in order, our pre-order, our post order. We often have something like a tree height or a tree node count that we can do, or a leaf count. Okay, we can have it destroy the tree, which will reallocate all the memory and all that stuff. We have a copy constructor and regular constructors. Those are the basic functions that we're going to have. Okay, and we can create functions for all of that, put it into an abstract data type, and then implement it however we want. Okay, so those are basic ideas. But if you do this with just a regular binary tree, you're going to run into a problem pretty quickly. Okay, so let's say that we have the following data. Okay, let's say we've got a 5, a 12, a 41, a 6, a 14, and a 2. Okay, if we want to add these to our binary tree, it's pretty basic that we'd start with the 5 here. Okay, it's really at the 5. So much better 5. A little better. Okay. But then there's no clear way we're going to keep adding this. Okay. I mean, early on, it's not bad. We could do one left for our 12. And we could do one right for our 41. But at this point, it's a lot to keep track of where the next one's going to be. So we have to have a left, left, and left, left, right. That's a lot. It really is a lot. Okay. So for that reason, and lots of others we'll talk about, we come up with this idea of a binary search tree, or BST. And what a binary search tree is, okay, there's a formal definition, kind of like we saw before. It has a root, and it's such that for every node, the left tree goes to a smaller value, and the right tree goes to a bigger value, okay, no matter what, okay, and that the left tree and the right tree are both binary search trees, okay. So this idea of left being smaller and right being bigger gives us an entirely new way to organize our binary trees, and it's clear what's going to happen, okay. So let's take a look at what we would do in this case. So we don't need that yet. So we start at the 5. We start at the beginning, okay. So the 12 is bigger than 5. So I'm going to go to the right and put a 12. Okay. 41, we start here again. 41 is bigger than 5. 41 is bigger than 12. Okay, so 41 is going to be down here. Okay, the 6, it's bigger than 5. It's smaller than 12. So the 6 is going to go here. Okay, so there's no question where it's going to go. The 14, it's bigger than this, bigger than the 5, it's bigger than the 12, it's smaller than the 41, okay? So the 14 goes here. Okay, and finally the 2 is smaller than the 5, and the 2 will go here. Okay, so it's also called a binary search tree because when we go to search for something in this tree, again, all we have is root. So there's no way for us to know without doing some calculations of some sort. There's no way to know how many nodes there are or anything about them, okay? But let's say I'm searching for that 14, okay? I'm going to start at root. That's the only place I know to start. And I'm going to say, is this the 14 I'm looking for? And it's not, okay? But because of this binary search tree nature, I know that if there is a 14, it's not going to be to the left. It's going to be to the right. So I go to the 12, okay? Same thing there. I can say, is this what I'm looking for? It's not. But if I'm going to find it, it's going to be to the right. I go to the 41, okay? And now I say, is this what I'm looking for? No. But if I find it, it's going to be to the left. I go to the 14. There we go. I found it, okay? For an unsuccessful search, say we're searching for a 3. I go to the 5. Is that what I'm looking for? No. If I find it, then it must be to the left. I go to the left. There's a 2. Okay, so the 3 would be bigger than that, but there's nothing there. There's no link there. So then I know that it's not there. Okay. So this binary search tree searching should sound very much like the binary search we do on an ordered array. Okay, it's the same idea. Okay, It's the idea that if we have a balanced tree, which we're going to get that whole concept eventually. So if we have nodes that are organized in this way, okay, no matter how many we have, again, balance means we have the same number of nodes on each level. They all have values. Okay, so there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So we have 15 nodes here. Don't know what that did. Went crazy. 15 nodes here. Okay, when we start our search and we search here, then we know we're immediately going to be able to eliminate either the left half or the right half. So say what we're looking for is bigger than this root node info, okay? So we know all these are gone, okay? So we're able to reduce the number of nodes by roughly half each time, which is going to give us the big O of n log n, okay? So it becomes pretty efficient, okay? And we're not ever having to sort, right? That the rules of the binary search tree mean that things are always going to be ordered. Okay, we're dealing with the ordering as we're adding things. Okay, so that will avoid us having to go back later and sort it. Okay, so that's good. We have good results there. Okay, the problem is that those good results depend on the tree being balanced. Okay, so in the worst case scenario, okay, if we were to enter the numbers 1, 2, 3, 4, 5, for example, in that order, into a binary search tree. Okay. So we start off with our 1. The 2 is bigger than that. We go to the 2. The 3 is bigger than that. We go to the 3. The 4 is bigger than that. We go to the 4. And the 5 is bigger than that. We go to the 5. Okay. When our tree looks like this, then the efficiency drops just to n. Okay, we have 5 nodes. In worst case scenario, we got to look at all 5 of them in this structure. If we're looking for, is there 6 in this table? There's no n log n here, right? We got to go check for 1, 2, 3, 4, 5. And only then we know that there's not a 6. Okay, so that's the problem that we run into. Okay, and then the solutions that we can have for that are varied. Okay, we're going to talk about a couple, one in particular. Okay, I think I'll make that a separate video, but to give you a preview of it, okay, we're going to call those Avl trees. Okay, so we've also added some complexities. The insertion's pretty straightforward here. The deletion can become a little bit of a problem. Okay, when we delete things, we have to make sure that those binary priorities of left and right still hold. Okay, so in the next video, we'll go through that code on how to delete. It turns out to be not as straightforward as the insert. Okay, so and then we'll also talk about the Avl trees. They're called self-balancing trees. Okay, and that's a way just to keep your tree as you're adding it to be balanced or nearly balanced. Okay, so that's the introduction to trees. Okay, this was a non-coding introduction to get the picture in your head of how these trees work and the ways we're going to be using them. Okay, so in the next video, we're going to be in the code. We'll talk about some code. We'll talk about the options. We're going to go straight to implementing a binary search tree, and then we'll move on to the Avl trees, self-balancing. Okay, so definitely more to come.